I am Dr. D.K. Tripathi, Assistant Professor of Physics under the Department of Basic Science and Humanities.
Since the first lecture, I am telling you that a very large number of atoms are gathered in the ground state and very less number of atoms are gathered in the excited state in any atomic collection. Now, we will prove it today. For proving it, we will have to take Maxwell-Boltzmann distribution law. Probably all of you know that there are three distribution laws. One is on the basis of classical mechanics called as classical distribution law, and it was developed by Maxwell-Boltzmann. That is why it is called as Maxwell-Boltzmann distribution law. And there are two distribution laws which are on the basis of quantum theory called as quantum distribution laws. First one was developed by Fermi and Dirac called as Fermi-Dirac distribution law, and second one was developed by Bose and Einstein called as Bose-Einstein distribution law. So from Maxwell-Boltzmann distribution law we can write n2 is equal to n1 into negative exponential to the power e2 minus e1 by kt. From that we will get n1 by n2 is equal to 1 by e to the power minus e2 minus e1 by kt, which will be equal to positive exponential e2 minus e1 by kt, where e1 and E2 are respectively ground state and excited state energy levels or energies. N1 and N2 are the number of atoms in the ground state and excited state respectively. K is Boltzmann constant and T is the temperature. Now from that what we know that E2 is very much greater than E1. Why? Because E2 is excited state energy. So this will give us n number of atoms, that is n1 number of atoms in the ground state, that is n1 is much more greater than number of atoms in the excited state, which is n. Let us discuss the Einstein's theory of stimulated emission, which is also called as theory of laser radiation. In the examination it is asked as interrelation between Einstein's A and B coefficients. Actually, from the first lecture we have discussed the three types of transitions qualitatively. Today we will discuss it quantitatively. So for that, let us start with the stimulated absorption or induced absorption or simply absorption. So what is this? If we take a collection of atoms, molecules, ions or particles, and for simplicity let us take the collection of atoms and ionizing it from outside. For that, if we irradiate this collection of atoms, molecules, ions or particles, then what are the possibilities that we discussed earlier? That there will be two energy levels. One is ground state and other will be excited state. Now let us assume that N1 is the number of atoms in the ground state and N2 is the number of atoms in the excited state. E1 and E2 are the energies of ground state and excited states, and K is the Boltzmann constant and T is the temperature. Then on what factor it will depend, we will try to find out. Okay, so for that we cannot keep track of all the atoms in this collection. So what we will take the unit volume of atoms. That means in unit volume what amount of atoms are there, how they are transiting from ground state to the excited state with absorption of energy, that means stimulated absorption, what amount of atoms are coming down from excited state to the ground state after completion of its lifetime, that is spontaneous emission. Amount of atoms will come down to the ground state under the influence of external energy, that is stimulated emission before completion of its lifetime or their lifetime to the ground state. So we will discuss them one by one. So as we have considered, number of atoms in the ground state is n1. Now let us take the tau AB as the time rate of transition of atoms from ground state to the excited state per unit volume, or this, you see what we are calculating, the rate of absorption per unit time per unit volume, that we will not be able to calculate it correctly or exactly. Why? Because in that collection of atoms, what we will do, that will be simply the possibility we are discussing. So this tau AB, what the probability of transition of atoms from ground state to the excited state per unit time per unit volume under the influence of external energy. Then this tau AB will be directly proportional to the number of atoms in the ground state. Let us call this as equation number 1. On what other factor it will depend? If I am asking you that what number of atoms will go to the excited state with the absorption of energy which is coming from outside, which we are giving per unit time per unit volume. So it depends on the number of atoms, what number of atoms are present in the ground state. Maximum they can be excited to go to the excited state. Now what other factor it will depend? It will also depend on the amount of energy you are giving. So if we take U nu as the energy density means energy per unit volume, because you are supplying the energy from outside, but you cannot keep track of all the atoms in the whole collection. So what amount of energy is falling to the unit volume which you have considered, that we will take. So this U nu is the energy density, which is what energy per unit volume. So this tau AB will also depend on the energy density of incoming radiation. If the incoming radiation is less energetic, or you can say, simply try to understand it, that if less number of photons will be available in the incoming energy, then less number of atoms will be excited, because each atom will require one photon to go to the excited state. Because just I told you that the photon will require the gap amount of energy to go to the excited state. Gap amount of energy means E2 minus E1, where E1 is the ground state energy and E2 is the excited state energy. As per Planck's quantum theory, this is h nu, that is one photon energy. So that is why each photon will require the gap amount of energy to go to the excited state. So if that means one photon, this means that tau AB will be directly proportional to the energy density of incoming. Now combining equation 1 and equation 2, we will get tau AB is directly proportional to N1 into U nu. From this relation, what we conclude, that N1 is directly proportional to tau AB. That means if there will be large number of atoms in the ground state, then rate of absorption will be high, and U nu is directly proportional to tau AB. What does this mean? That if the incoming radiation is highly intense, then rate of absorption will be high. If it will be less intense, the rate of absorption will be less. But to which extent this number of atoms and the energy density of incoming radiation will affect the rate of absorption per unit time per unit volume, that cannot be determined. So to know it quantitatively, we will have to bring the equality sign in place of proportionality sign, and for that we know that to bring the equality sign in place of proportionality sign, we will have to take a constant. But this constant will not be any constant. This constant is defined by Einstein himself. Einstein has told that if the constant is taken for any natural transition, then it will be A, and if the transition is induced one, then the constant should be taken as B. Now, if we consider that ground state level as the mth level and excited state level as the nth level, then here tau AB will be directly proportional to a constant Bm2n. That means we are telling that from which level the transition start and to which level it is terminating. Here the transition start from nth level and it terminates to nth level. So nth level will be written at first and then nth level will be written later on. This can also be written as Bm2n, but you should not write it Bn2m, because if you will write Bn2m, then it will be error in the fundamental. The energy state, which is always excited energy state, that is nth level is excited state, so the absorption will not start at that level. So please keep in mind that Bm2n will be written. It will not be written as Bn2m. Tau absorption, that means the rate of absorption, will always start from the ground state and it will terminate to the excited state. So because of that, here we will write Bm2n into n1 into u nu, where Bn2m is constant of proportionality, and this is known as Einstein's coefficient of stimulated absorption. So let us discuss spontaneous emission quantitatively. What is spontaneous emission? If the atoms in the excited state completes their lifetime, that is 10 to the power minus 8 seconds, they fall down to the ground state with the emission of the energy. So this is called as spontaneous emission. So here we will try to find out that on what factor the rate of spontaneous emission will depend. If we take tau Sp as the rate of spontaneous emission per unit time per unit volume, that means out of unit volume of atoms, how many amount of atoms or how many atoms will complete their lifetime and will come down to the ground state without any influence. So if tau Sp is the rate of spontaneous emission per unit time per unit volume, it will depend on number of atoms present in the excited state. Why? Because what number of atoms are in the excited state, maximum possibility will be that all of them are completing their lifetime and coming down to the ground state with emission of the energy. So tau Sp will be directly proportional to N2, but it will not be influenced by the external energy, because these atoms are completing their lifetime and then they are coming down to the ground state with emission of the energy. That means it is a natural transition of atoms from excited state to the ground state. So for that the constant will be taken as A, as Einstein has defined it. So this will be equal to An2m, because the transition starts at the excited level, that is nth level, and it terminates to the ground state nth level. So that is why we will write it An2m. You just take in mind that you cannot write it as Am2n, otherwise this will mean that the spontaneous emission occurs at the ground state. This is never possible. So tau Sp will be equal to An2m into N2.
These are some of the references which you must pursue to know more about the topics. Thank you.